Welcome back, everyone. Today we're going to be talking about goodness of fit tests. A goodness of fit test is a method that we can use to compare observed frequencies to what we would expect from a simple probability model stated from our null hypothesis. If you recall, we've already talked about a binomial test, which is one form of a goodness of fit test. But if you remember, it's limited to only two possible outcomes, either a success or a failure, or if you want to think of it more generally, that we need to be able to classify our observations as either being in this category or that category. So what about situations where we have more than two possible outcomes for our observations? Well, that's what we're going to talk about today. And what we're going to talk about then is what's called the chi-squared goodness of fit test, which compares observed counts in each category to a discrete probability distribution. We'll get into this probability distribution in a little bit more detail later. But if you remember from our descriptions of data types, we talked about discrete numeric variables. And these are usually counts. These are whole integer values where we can't have values in between those integers. So for example, we might have counts of the number of flowers in a square meter of field, or counts of the number of offspring produced, or perhaps the number of wildfires within a year. And so we're going to use this distribution as a way of modeling the counts of the number of observations in each of our categories. Now, in this chi-squared goodness of fit test, it's important to recognize that the x is the Greek letter chi, that in the English language is pronounced as chi and not chi or chai. Rather than trying to start by explaining the test, what I thought I would do today is to work through an example and explain how the test is done through the use of this example. So as many of you might know, I'm a Canadian and I like hockey. And so what we're going to talk about today is this interesting distribution of the number of hockey players in the NHL, the National Hockey League, that are born during each month of the year. So this is a sample that was collected from the NHL's website of 1,245 NHL players and the month that they were born in. So you can see that most NHL hockey players are born in January, the fewest in November. So here we have each of the 1,245 observations being categorized into one of these 12 categories corresponding to each of the months. So our variable then is birth month, which is an ordinal variable that has 12 categories arranged in this particular order. And we classify each observation or each hockey player into the month in which they were born. Now, anytime we test a statistical hypothesis, we follow four basic steps. We first start by stating the null and alternate hypotheses. We then compare the observed data to the null distribution using something called a test statistic. We use this to then determine the appropriate p-value. And once we've calculated our p-value, we can compare that to our alpha or our significance level and draw the appropriate conclusions. So what are our hypotheses in this case? Our null hypothesis in this example then is that the probability of an NHL player being born on any given month is equal to the national proportions. What I mean by this is that NHL hockey players are no different than the average population in terms of when they're born. The alternate hypothesis is that the probability of an NHL player being born on any given month is not equal to the national proportions. So here what I've done is to simply depict the same data in a table format. But what I'd like to do is explain a little bit more about what I mean by in proportion to all other births in the population. So here we have data for all births in Canada, and we can see that 7.94% of all births in Canada occur in January. So what our null hypothesis is suggesting then is that the proportion of NHL hockey players born in each of these months will be the same as the proportion of all Canadians born in each of these months. So you can see that there's not an equal probability of being born in each of the 12 months. It seems like most offspring are born in May in Canada, and the fewest offspring are born in February. So these are the null proportions that we want to use to test whether or not the observed proportions differ from those null expectations. So how can we then compare these observed counts of observations in each of the 12 months to what we would expect based on the proportional births in the Canadian population? Well, to do this, we would take our total sample size of 1,245 and for January, multiply it by 0.0794 because 7.94% of all births in Canada occur in January. And when we do that, we can calculate that we expect that 99 out of these 1,245 NHL hockey players would be expected to be born in January if the births of NHL hockey players was proportional to the overall population in Canada. And we can do that for each of the 12 months in the year to come up with our expected values of births in each of the 12 months. Now, in this case, to keep it simple, I've rounded these to whole numbers, but normally when you calculate your expected values, you would retain the decimal places in your calculations. So we have our observed statistical sample, and we have what we would expect to see if the null hypothesis were true. But now we need to do what we always need to do in a statistical test, and that is to sort out what differences would we expect to get between observed and expected values just by chance, just due to sampling error, if the null hypothesis were true. And to do this, we need to calculate what's called a test statistic. In this case, the test statistic that we're going to be dealing with is called the chi-squared test statistic. And this chi-squared test statistic is calculated by summing up all of the squared differences between the observed value for that month and the expected value for that month, divided by the expected value for that month. So for each of the 12 categories in this example, where K is 12 for 12 categories, for each of those 12 categories, we take the observed value, subtract the expected value, square that difference, and divide it by the expected value. And so we add all of those up across the 12 categories, and that gives us our chi-squared test statistic. So this chi-squared test statistic measures the discrepancy then between our observed frequencies from our data and the expected frequencies from the null hypothesis. Now, some of you have probably encountered this formula already for the chi-squared test statistic and think to yourself, oh yeah, right, observed minus expected squared divided by expected. I've got this, okay? And so you might have memorized this formula in the past, but I want to pause and think for a minute about why we use this particular calculation for this type of data. Why don't we calculate our test statistic in some other way? Well, test statistics are actually really important in statistics. And what our smart statisticians have figured out is that certain measures for certain types of data follow really predictable patterns when the null hypothesis is true. And these certain measures for a particular type of data are what are called test statistics. In this particular situation, where we have counts of observations in each of a bunch of categories, we know that just by sampling error, our counts in each of those categories is going to differ from sample to sample, even when the null hypothesis is true. But what the smart statisticians have figured out is that if we calculate a value like this, observed minus expected squared divided by expected summed across all of the categories, then this calculated value, this test statistic, follows some really predictable patterns that can allow us to calculate what the probability is of getting test statistics of certain values. So for example, if we look at what this theoretical distribution of chi-squared values is, this is what it looks like. When we have 12 possible categories, when the null hypothesis is true, most of the time our chi-squared value is going to fall in and around 10. Sometimes it's going to be really close to 0, but just by random chance, the number of counts in each of those categories is not going to be perfect. It's going to bounce around a little bit. And only very rarely are we going to get a chi-squared value that's, say, above 20. Okay, so when we have 12 categories, our chi-squared distribution looks like this. And this comes from the smart statisticians who have figured out the theory. Now, in this case, you might have noticed that I've got in the title here that the degrees of freedom in this distribution are equal to 11. And that's really important because chi-squared distributions depend on their degrees of freedom. Well, what do I mean by the degrees of freedom? Well, the degrees of freedom are part of what shapes this distribution. And in a chi-squared goodness of fit test, the degrees of freedom are calculated by the number of categories minus 1. So in our example, we had 12 categories corresponding to the 12 different months. And so the degrees of freedom in our example of the NHL hockey players is 11. And so you can see that I've redrawn this frequency distribution for a chi-squared distribution with 11 degrees of freedom in green here. And you can see, as before, the most likely value when the null hypothesis is true is that the chi-squared value is going to come out around 10, and values greater than 20 are really pretty unusual. But here we have a different distribution of chi-squared values when the null hypothesis is true, and we have 6 categories corresponding to 5 degrees of freedom. Then most of the time we're going to get a chi-squared value that's actually really quite small, and only rarely will it even be greater than 10. And finally, this blue distribution is a chi-squared distribution where we have 20 degrees of freedom, or in this case, 21 categories. Okay, so this is why we calculate our chi-squared value as our test statistic, because this test statistic has really predictable patterns that depend on how many categories we're talking about. So let's go ahead then and calculate our chi-squared test statistic from our sample. So if you remember, we're going to sum up across all of the months what the observed value is minus the expected value for that month squared divided by the expected value. So if we take January as our first example for I equal to January, the observed value was 133 players in the NHL were born in January. We expect, based on the proportion of births in the broader Canadian population, that we would have expected that of our 1,245 hockey players, that 99 of them would have been born in January. So observed minus expected, that difference is going to be squared, which is 1,156 divided by 99. Now, if you remember, to keep things simple, I've rounded the expected values here to whole numbers, but normally we would maintain those decimal places in our calculations. All right, so this is our value for January that we just calculated. This is February, March, April, and so on. And so if we sum up all of these calculated values, all the way from I equal to 1 through to I equal to 12 for the 12th month of the year, and we sum those all together, we can calculate that for this sample, our chi-squared test statistic was 44.77. So what do we do with this number? Is this an unusual number? Is this a surprising number? Is it a big number or is it a small number? Well, to determine whether this is an unusual value, we need to compare our observed test statistic to what we would expect to find if the null hypothesis were true. So we go back to our theoretical chi-squared distribution with 11 degrees of freedom because we had 12 categories. And we can see that most of the time when the null hypothesis is true, this chi-squared value is going to fall in and around 10 when we have 12 categories. And only very rarely is that chi-squared value going to get up above 20 or 30. And here is our observed test statistic way out here, 44.77. So this is almost never going to happen when the null hypothesis is true. We can see that from the distribution and the very low value of the distribution here. But if we wanted to calculate an exact p-value, we could do this in one of two ways. Here I've just indicated some code from R that uses this function called p chi-square, where we enter in what our calculated chi-square value is. This is a q. Okay, we specify the degrees of freedom, and we specify that we don't want the lower tail of the distribution. We want the upper tail of the distribution. So lower tail equals false. And if we do that, we calculate a very, very small p-value, 5.3 times 10 to the minus 6. So it's really unlikely to get a test statistic this big when the null hypothesis is true. Another way that we can assess the p-value based on our test statistic is to use a table of critical values. Critical values are simply the value of the test statistic when p is equal to our significance level, or alpha. So here we have along the left-hand column the various degrees of freedom. Across the top, we have our different alpha levels. And so here I've just highlighted in blue an alpha of 0.05 just by convention. And we can see that the critical value for our chi-square test statistic changes depending on our degrees of freedom. So in our case, we had 12 categories, so 11 degrees of freedom. And our critical value then for our chi-square test statistic is 19.68. When we calculate a chi-squared value of 19.68 with 11 degrees of freedom, then our p-value is going to be equal to 0.05. So if our calculated chi-squared value is greater than this critical value, then that means that the p-value will be less than 0.05. So here we have this same chi-squared distribution with our critical value indicated here at 19.68. And what this figure shows then is that 5% of the distribution, 5% of the area underneath this curve falls to the right of this critical value. And that means that there's a 5% chance of getting a chi-squared test statistic of 19.68 or greater when the null hypothesis is true. And so any chi-squared value greater than 19.68 will mean that there will be a p-value of less than 0.05. And in our case, our test statistic was 44.77, way over here, which means that the p-value was much, much smaller than 0.05. Okay, now there are a couple of important things to point out about this distribution. The first is that anytime we calculate a chi-squared value, it's always going to be positive. It can't be negative because in the numerator, if you remember, we squared that difference. So that squared value means that it can never be negative. So chi-squared values are always positive. The second important thing to note is that even when we have an alternate hypothesis that is not directional, a chi-squared test is always one-tailed. We're always interested in this upper tail of the distribution for our chi-squared goodness of fit test and not the lower end of this distribution. So now that we've calculated our p-value, we need to draw an appropriate conclusion. So our p-value was very, very, very small and well below the significance level of 0.05. Or alternatively, we could determine that our test statistic was much greater than the critical value of 19.68 that occurs for chi-squared distribution with 11 degrees of freedom. So in this case, these tell us that our results would be very unusual, very, very unusual if the null hypothesis were in fact true. And so instead, we make the parsimonious conclusion to instead reject the null hypothesis and accept our alternate hypothesis. So in this case, biologically, NHL players are not born in the same proportions per month as the Canadian population at large. If we look at this side-by-side bar plot, we can see that the observed values exceed the expected values early in the year and fall below the expected values late in the year, which indicates that NHL hockey players are much more likely to be born in the earlier months in the year than the later months of the year. Or put another way, you have a much better chance of making it into the NHL as a hockey player if you're born earlier in the year. As with any statistical test, there are a number of assumptions that must be met if our inferences are going to be correct. The first assumption is common to all statistical tests, and that is that our statistical sample was collected randomly and that observations within that sample are independent of one another. With respect to the chi-squared test, this test assumes that no category has an expected value of less than 1, and that no more than 20% of the categories have expected values less than 5. If you find that either of these latter two assumptions aren't met, one way to solve this problem is to lump together categories that make some logical sense to lump together in order to test your hypothesis. So in this video then, we've covered several important lessons. The first is that we can use a chi-squared goodness of fit test to determine whether counts in categories differ from a null distribution based on null proportions. But we've also learned about some other more general lessons. The first is that test statistics differ depending on the type of data that we have. And the reason we calculate different things for different types of data is that these different test statistics are really useful because they have predictable properties when the null hypothesis is true. And so we can use these calculated test statistics to determine whether our sample was unusual or not relative to what we would expect from the null hypothesis. So in this case, when we have counts of the number of observations in different categories, the appropriate test to use to determine whether the distribution of those counts across the categories is unusual relative to our null hypothesis is the chi-squared goodness of fit test.